Welcome back to Lecture 12. Today, we are diving into the mechanics of Monte Carlo methods, with a specific focus on walking step by step through your coding implementations and transformation exercises. At its core, the Monte Carlo method is a numerical technique. We use sequences of random numbers to calculate probabilities and simulate complex natural systems that are entirely stochastic. In high-energy particle physics, we rely on this method to run two massive stages of simulation. This is the first stage, event generation. You're looking at the exact moment particles collide, generating a chaotic burst of secondary particles. But theoretical physics output must be tested against physical reality. This view shows the second stage, detector simulation. Simulated particles are tracked interacting with the physical boundaries and grids of a lead glass calorimeter. Because quantum interactions are entirely random, our massive deterministic computer simulations are useless without a reliable mathematical engine for generating statistical chaos. In principle, we could track natural randomness, like throwing dice, counting cosmic muons, or timing radioactive decay. But doing that millions of times per second is computationally inefficient. We have to fake our randomness using algorithms. The bedrock of these algorithms is the linear congruential method. It relies on a repeating equation containing a multiplier, an increment, and a modulo operation. Every chaotic sequence needs a starting point, called the seed, or x0. The final step is converting the integer output into a usable probability. By dividing our resulting value by the modulo, m, we convert the sequence into a uniform range precisely between 0 and 1. That uniform 0 to 1 range is the raw material for every complex physics simulation we will build today. Our first major computational pitfall is periodicity. Because the modulo method is completely deterministic, the sequence of numbers will inevitably repeat itself. In exercise 1, we test this logic in Python. If we choose a small modulo, like 10, the algorithm creates a highly repetitive sequence that cycles the same few digits endlessly. It's mathematically useless. Exercise 2 corrects this by implementing randu. By allocating a 32-bit integer for our modulo, 2 to the 31st power minus 1, we push the periodicity out to computationally acceptable levels. This chart shows the distribution of 100,000 generated values. The flat, even distribution proves the sequence remains perfectly uniform across a massive sample size. A quick warning for those working with legacy codebases. The obsolete C++ rand function returns a raw integer. You must remember to manually divide that output by rand max to normalize it back to that 0 to 1 range. But a flat 0 to 1 distribution does not describe physical reality. Whether you are modeling a decay angle or a dice roll, we have to scale that raw output. To map a uniform 0 to 1 output to any arbitrary continuous range between limits a and b, we applied this scaling formula. If we need a random particle decay angle ranging from 0 to 2 pi radians, we substitute our limits, leaving us with a simple variable assignment. Phi equals 2 pi times our random number, r. For discrete step-based events, we use an integer formula, mapping to a range defined by m and n. Simulating a standard 6-sided die roll simply becomes 1 plus the integer value of 6 times r. Scaling translates our raw computational math into physical dimensions, letting us model continuous geometry or discrete events accurately. With basic scaling covered, we can move into simulating physical hardware limitations, specifically an electromagnetic calorimeter, or ECAL. This diagram illustrates the ECAL principle. Measured photon energy is directly proportional to the number of electrons generated in the hardware shower. Because counting those secondary electrons is an inherent statistical process, it carries a strict counting uncertainty. That uncertainty is proportional to the square root of the number of electrons. Therefore, the fractional energy resolution scales inversely with the square root of the total energy. We apply this in exercise 5. We need to simulate a 20 giga-electron-volt photon hitting the Atlas detector, which has a known stochastic term of 0.10. To find the specific standard deviation for this hit, we multiply the 0.1 constant by the square root of 20. Now we apply a concept called smearing. To simulate a realistic measurement, we do not record a perfect 20 GeV. Instead, we draw a random number from a Gaussian distribution centered at 20, utilizing our calculated width for the deviation. In Python, the root framework handles this complex math under the hood, with the rnd.gauss function, passing in our energy and sigma values as arguments. This chart shows the results of looping that simulation 100,000 times. The red bell curve plotted precisely over the blue distribution bars perfectly mirrors the physical hardware variance we expect to see in the detector array. By combining our scaling variables with Gaussian smearing, a few lines of Python code successfully replicate the physical imperfections of a multi-billion-dollar machine. That brings us to our final challenge. What do we do when our physical system doesn't plot out as a uniform flat line or a neat Gaussian bell curve, but instead requires a completely custom probability density function? We use the transformation method, also known in statistics as inverse transform sampling. Step 1 relies on the conservation of probability. We set our uniform random distribution equal to our target physical distribution, f of x. Looking at these plots, the middle graph shows our initial probability density function. Step 2 states that if we integrate the area under that curve from its minimum bound to x, we generate the cumulative distribution function, seen in the bottom plot. For step 3, we set this newly generated CDF equal to our uniform random variable r, and use algebra to find the inverse function, explicitly solving for x. Let's apply this to exercise 6. We want to sample from a linear distribution defined by f of x equals 2x, bounded between 0 and 1. We evaluate the integral of 2x dx from 0 to x. The integral of 2x simply resolves to x squared. We set that result equal to r. Finally, we invert the equation to solve for x. The result is x equals the square root of r. Taking the square root of our flat, uniform computer numbers perfectly models our 2x physical distribution. You apply this exact same workflow to the exponential decay exercise. The starting probability density function for exponential decay is 1 over tau times e to the power of negative t over tau. Integrating that expression from 0 to t yields the cumulative distribution function, 1 minus e to the power of negative t over tau. Set that equal to r. To algebraically isolate t, we have to use the natural logarithm, which leaves us with the final inversion. T equals negative tau times the natural log of r. This specific natural log operation is highly optimized. It's the same mathematical engine hiding inside the Box-Moeller algorithm used by software libraries for standard normal distributions. The transformation method allows us to take raw, flat probability arrays and accurately mold them into the complex curves of any physical reality we need to measure. Let's consolidate this. For your exams and practical coding sessions, you need to lock down 3 high-yield tools from today's exercises. First, do not drop points on simple uniform scaling. Memorize a plus b minus a times r for continuous variables, and m plus the integer of n times r for discrete events. Second, remember that hardware error simulation relies on Gaussian smearing. Because counting particles is a statistical process, your standard deviation calculation will almost always involve the square root of the system's energy. Third, when faced with a custom probability curve, write down the 3-step transformation algorithm immediately. Integrate your function to find the CDF, set it equal to r, and invert to solve for x. These 3 tools are mandatory. Without them, physicists would have absolutely no way to validate the petabytes of raw data pouring out of collider arrays at facilities like CERN. Monte Carlo methods translate the rigid logic of computer science into the beautiful stochastic chaos of particle physics. So practice those complex integrals, carefully review your scaling logic, and I will see you all in our next physics session.